Hello and welcome to the Explaining Rust Analyzer video series, where we try to learn how Rust Analyzer works one crate at a time. Last time, we looked at the general infrastructure for parsing, especially at the events and how we use them to transform the tree from the shape you see when you actually parse the code to the shape you want to have in an ISD. What I want to do today, at least what I want to do to start doing today, I'm not sure if we will finish in one lecture, is to look at how actual parsing work. Finally, we will be looking at the meat of a parser. And that's a very interesting topic. Why? Because this is one of the systems where an IDE like Rust Analyzer differs pretty significantly from traditional batch compilers. This is a complement to the difference in the syntax tree. If you remember, a couple of weeks ago, we looked at the raw one and those lossless weekly type syntax trees, and that was kind of like one piece of the puzzle to allow you to represent the code with arbitrary errors. The other piece of the puzzle is the actual parser, which doesn't just like fail on an erroneous import, but somehow recognizes valid syntactical constructs. I like to say that this is an error resilience property of a parser, which is different from error recovery. Error recovery is when you see some bad input and you try to understand, hey, what the user meant to write here, and you try to repair the input to make some sense. While error resilience is when you like see invalid input and you just don't care about it. You just try to parse it in the you just try to parse it as best you can. You try to find the biggest valid syntactic substrings in this input. So another reason why this is interesting is that because I really like how the parser is written in Rust Analyzer. I feel that that's like a great way to write parsers, at least in some circumstances, because the code is simple, the code is really readable, and the code is very pedestrian. It has very little abstractions, and in general, it's just kind of like baby code. And at the same time, I haven't seen this style of parsing discussed elsewhere, and I don't even think I've seen any parser which is implemented exactly like this. Like the closest thing is JetBrains PSI builder infrastructure, which is very much the primary inspiration for this style of parsing. But that is a little bit more elaborate, but like that's mostly because of like using Java. In Rust, we were able to create an actually really nice API here. So before we begin, I want to answer like the big question is, why are we even writing the parser by hand? Why are we not using, and yeah, we are writing like a recursive descent parser by hand. Why are we not using some well-known techniques for generating parsers like a ladder parsing or like parsing expression grammars or something like that? And that's a very good question. The best answer to this type of question is this recent post by Lawrence Strutt, where he basically describes the modern landscape of various parsing techniques and describes their benefits and drawbacks. And what is specific in our IDE use case, at least while we haven't merged with the main compiler, is that we are parsing an existing language. So we are not designing a language grammar. We need to parse something which was designed before us. So in Rust Analyzer, we don't particularly care about grammar correctness. It, of course, would be nice if we produced exactly the same parse trees, exactly the same, and we accept exactly the same set of strings as RASC. But practically for an ID use case, if in some edge case you parse differently, it doesn't really matter. And that is like an important point, because if you do care about your language actually having proper grammar, which is unambiguous and which is, well, exists in some form of specification, you probably do want to use a parser generator, which not only gives you a parser to actually parse the language, it also gives you a proof that the grammar for your language is actually unambiguous. And that's kind of like the big reason for using parser generators when you design languages. However, if you only want to parse a language and you only want to parse one language, then writing the parser by hand, and yeah, you want to parse language, you want to parse only one language, and you do not super critically care about parser being correct. So you are not defining the language and you are not doing this in a security sensitive context. Then parsing by hand is actually an option, because turns out it's not that hard to parse strings by hand. What hard is making sure that your grammar is correct. But if you like following some other grammar and if you tolerate minor discrepancies, like doing by hand, it's not that hard. And an additional consideration here is that in Rust Analyzer, we want to be resilient to errors. And error resilience and error recovery historically has been major pain points of parser generators. I think the Akamel parser generator, Merlin, actually has, or is it, okay, it's not Merlin, it's like Menhir, I don't know how it's pronounced, but basically like the Akamel parser generator. That actually has some really fancy techniques for generating really top-notch error messages, but I'm not sure if those techniques are applicable to error resilience. I'm not saying that doing error resilient LR parsing is impossible. It's just that I haven't seen that implemented, and I've seen recursive descent being used with great success at JetBrains for error resilience parsing, so that's why I went with it for Rust Analyzer. So yeah, and actually, while we are like have browser open, let me also show you how the Kotlin does the parsing, or rather where you can look at the actual parser. So this is like the Kotlin repository, and there is this like Kotlin parsing or Kotlin parser stuff, basically like this directory which contains some amount of code, but not a lot of it. And for example, like in Kotlin expression parsing, you can actually see like the actual parsing code. The reason why I'm showing Kotlin is that if you want to learn how to write parsers for IDEs, that is probably the best source to learn from. You don't need to understand a lot about underlying IntelliJ infrastructure to understand it. This code is like really readable and really simple. And the code in Rust Analyzer is very much inspired by it. It is not as good as Kotlin's code in terms of error recovery. So you kind of like might want to combine looking at Rust Analyzer and looking at Kotlin. And personally, when I see some IDE-specific bug in our parser, like when I want to tweak error recovery, the first thing I do is that I fire up IntelliJ and look how Kotlin handles this case. And if Kotlin does handle this case, then I look at the parser and try to understand how it works. Okay, without further ado, let's actually look at the parser. So let's go to the Rust Analyzer repository and let's actually go to the main branch and update it. Yeah, and I've actually been cleaning up bits of a parser before this video, just so that I'm slightly less embarrassed by showing this to you. So let's go to this crates. Parser, and here we want to start with lib.res. Okay, So if I recall correctly, we covered everything except like the parser and the grammar. So let's first start with a parser. The parser defines the structure, the state we use during parsing. Here are the following bits of states. First of all is like the source of tokens. If you recall, we write parser in such a way that it is abstracted over a source of tokens. And in particular in Rust and Ledger, the tokens can come either from the text or from token trees during macro expansion. So that's why we have like this trait here. What parser produces is the set of events, which describes the shape of a tree while we are traversing it. And if you want to learn more about events, then please watch the previous video. And there is like this third thing, steps, which is not really important, but actually it's a good case in point to illustrate that we use assertions in our parser a lot. And when you write parser by hand, one of the bad cases you can hit is that you might accidentally write an infinite loop inside the parser, so that on some specific input, the parser just tries to parse something again and again and again, and it is stuck. And this steps field is what prevents us from hitting these stuck situations. Basically, it is like a very stupid way to determine an infinite loop. So in general, like if you have some kind of like a thing, a graph, and you want to find a loop, like the proper way to do this is to traverse the graph and record the stack of nodes which are active, and when you visit a node and it is currently active, you understand that, hey, this is a loop. But like that's like complicated and needs like state and all various kinds of special conditions in the code. A simpler way to kind of like detect the infinite loop is just to count the number of steps you took to process the thing. And if at some point you realize that you have made kind of like 1,000,000 steps, then you just assume that you are in the loop because, well, everything should have finished long before that. And that's exactly what we do in the steps. So every time we look at a token, we increment the steps. And if we made 10 million steps while parsing a file, we kind of assume that we are in an infinite loop and just panic there. And it's much easier to debug a panic than to debug an infinite loop because, well, you immediately have a stack trace, how you get there, etc., etc. So yeah, steps is a nice trick. And a more general idea is that we use assertions in parser a lot because it's very easy to like basically like the essence of parser is transforming from an unstructured input into a structured input. And when you are working with structured input from the start, you usually don't have a lot of opportunities for assertions. Basically, every time you do want an assertion, you actually might want to encode that assertion into types to make it impossible at runtime. So like instead of like asserting that something is not none, you just like use a match, that kind of things. When parsing, you start from unstructured data, and this is like fundamentally a place where you create assertions, where you create facts which assertions can rely on. So it is much more dynamic and much easier to get around, and you cannot just like add types there. Because fundamentally what are you doing? You're basically assigning types to the input. Okay, so this the parser struct. It contains a bunch of methods. An important point here, though, is that these are strictly the methods for consuming the tokens. There is no methods for like parsing anything. So if we type self like parse, you know, like there's no like parse expression, there's like no expression, etc., etc. Everything here is strictly about consuming input and producing output syntax tree. So we create a parser the result of a parser is a sequence of events. During parsing, you can expect the current token. You can expect inspect a token with a look ahead, and look ahead is constant bounded. You can conveniently check if a token is a specific kind of token. In Rust, there is this complication that the Alexa produces this token as two separate tokens with an extra flag that there is no white space between them. So we need to take care, and if we need to take care of for calls like self at shift left, because here we want not only to check like one token, but we want to check a token, a white space after that, and the next token, and that's what this code is doing. This method eats one token and returns boolean dependent on whether it ate the token or not. And yeah, another interesting thing is that it actually does this gluing of tokens. To get back to this shift left example, the subtle thing here is that Lexer gives us two tokens, two less than signs. But in the syntax tree, we actually want to see a single token, a single shift left token. We don't want to see a shift left node which contains of two tokens. Basically, like some tokens are context sensitive. And this android tokens is exactly the mechanisms we use to glue the tokens. So if, for example, our token is shift left, then this say that it contains of two raw tokens, and then in this do-bump method, we actually emit an event which produces one token, but using more than one underlying token. Okay, we've seen add composite like that deals with its case. Add token set. Reminder, token set is basically a bit set of tokens. So add TS checks if the current token belongs to the token set. Add contextual keyword. Again, some keywords are not always keywords like union or default. And we actually need to use like this extra method to check if this is this particular keyword or not. The next, okay, yeah. The next methods are interesting. They actually allow us to create a syntax tree. So the start corresponds to start event, and it opens a syntax tree. Then bump and, rather than it, bump any can be used to actually add token to this currently open syntax node. And of course, you can, if you have nested calls to start, you have nested nodes in the output. And yeah, this marker thing is interesting. So what it is essentially a node which is currently being parsed. And in this marker, you actually have this complete method which says that the syntax node has finished and now has a specific syntax kind. So like it's interesting that you say what kind of syntax node it is, not when you start parsing it, but when you finish parsing it. And the reason for that is that at the start it might not be clear what exactly are you parsing. Is this like an expression or a type? But then after you've actually parsed the thing, you may later realize that, hey, this actually was an expression. So let's emit an expression there. This is like a little bit confusing. So this API needs some time to wrap your head around it. And that's why I actually don't want to go too deeply into the details of this API. But rather, I'd just show how we use this API. Okay, yeah, it's a token and it returns a boolean whether it ate token or not. Bump, it's the token unconditionally, and it's interesting that it takes as an argument a kind of token which it is supposed to advance over, and this is purely an assert. So if you are writing a parser and you expect that, hey, I want to advance over like a specific kind of token, you use bump method, and this will assert, this will check your assumption. Bump any is a counterpart which actually bumps over arbitrary token, but this is rarely used. Okay, a bump remap is how we handle contextual keywords. Basically, you remap the identifier to the actual keyword kind. Then we have some error reporting functions. So error just emits an error at the current position. Expect emits an error if the current token doesn't match the kind. And those are about error recovery, which I guess we will cover separately. So again, interesting points here is that parser doesn't actually parse things. It is like a bit of misnomer. It only advances over the input, looks at the tokens, and constructs the syntax tree. The actual parsing happens in the grammar module. And yeah, just like the doc commands say. And this grammar module looks very much like formal grammar in a domain-specific language, in an embedded domain-specific language. So it is like written in like very simple, a little bit unusual style, and let's just actually look how it works. So first of all, we have a bunch of entry points here. And the reason for that, you sometimes, like in Rust, you want to invoke parser in two cases. First, when you just parse a file, and that's the main source file entry point for. But when you parse macros, you have things like $x expr, and here you want to invoke parsing function which parses not like a file but an actual expression, and that's why you have like this entry function here. So let's look at the parsing. We parse source file. First, we start a new marker. We start a file syntax node. And when we will have parsed the file, we will have called a complete method, which closes this marker and assigns it a type of a source file. So everything between those two will get attached to the source file. And if we open syntax tree, we will indeed see that the topmost node is a source file. This shebang token is an interesting thing. You can actually have hash banks in Rust files, so that things like Rusty, or I don't remember how it is called, like basically like a thing which allows you to execute Rust file as a script, just work. And this is supported in the parser, and here we see that this just gets attached to the syntax node for a source file. Okay, so we start the node, we add this hash bank, and then we parse mod contents. So notice that this is in the items module, and this items module declares here. Every module in the grammar starts with declaring submodules, and then it always uses star import from parent module. In general, I hate star imports. I never ever use them, but in the grammar, this is the single place where we use it everywhere. In like if you open any file here, even like nested like expressions atom, you see that they start with this u star. And that is because grammar is recursive. You can call every production from every production. And I deliberately want here to be a single namespace of all the grammar productions. So if we look at items file, basically every function here you can think of as a production in a grammar file. And if it is marked as pubsuper, if it is not private, it can be used everywhere. So let's see how we parse module contents. The first thing to note here is that before this function, we have this special comment. And this comment is actually a test. So it starts with a special word test, and then it has the name of the test. It usually corresponds to the name of the function which test is for. And then it contains a bunch of functions. Contains like just some Rust code. This comment gets read by a special thingy. And then gets copy-pasted into this test fixture in the syntax test data parser inline OK. Alongside this fixture, we have a Rust IST file, which contains not what I want. Which contains the expected parse tree for this file. So the way the test works is that it just parses this fixture and compares an IST with what we have saved as an expected IST. And if there is a difference, you get notified about it. So this is a kind of expectation tests. Actually, let's look at this. Yeah, this is called Parser test, and it's like kind of simpler than it looks like. So basically, we walk through. Okay, that's interesting. That's actually yeah. So like the test contains of like two bits. The first bit actually just runs whatever fixtures there are in the test data directory, and that's what we're looking at. And here we just like parse file and debug dump the IST, and then this like driver function compares, like using actually an expectation testing library we use in Rust Analyzer, expect test, to like compare that the result is what we expect. And I think separately there should be that's also a fun test. It basically checks that Rust Analyzer can actually parse its own code. And where is... Yeah, anyway. Like what I'm looking right now is another bit of code which actually fails a test if we create a new test. So let's actually add a test for this inner attributes. Inner utter. And let's run the test. A confusing thing. the parser itself is in crates parser, but the tests for it are in crate syntax. This is accidental. I should move the test to parser someday, but it's like not super trivial. There's that. Okay, so we see that it actually fails in source gen parser test. I don't think we covered code generation in Rust Analyzer yet. So we should do it some other day because it's like we use it for all things and for this test as well. So what this part of the test does is that it reads the grammar, extracts all the commands from the grammar, and then where is the comment extraction code? Okay, yeah, like this is, yeah, so like here, like we extract the comments, we get all the Rust files, and then in the process file, we do collect tests on the text of this file, and this like extract all the comments block and looks for the blocks which contains tests, etc., etc. Basically, what this does is like collects all those like test comments and writes them as a file in this like test data directory. So why like I'm like using this like strange infrastructure for testing which no one else like understands? The reason for that is it gives you very powerful ability. It gives you an ability to put an example of what are you parsing right next to the code which does the parsing. So if we, for example, look at something like, I don't know, let's like look at generic arguments. Yes. So if we look at like the parsing function for generic argument, you see that there is like a lot of conditions here. Like this is like a complicated function. But, oh, like this test I should have removed to not show you because it's like not how you should do it anyway. But here, like you can see, okay, so this is generic arg, and this is a test for a function. So you understand that, hey, like this is what this function is parsing. Like it's like it's not super clear like what exactly here is a generic argument, but like if you think about it, well, like only this thing is generic argument. So this like gives you a context about what is happening here. And for example, like if you like look here, so there's like this condition, like we check for like some tokens, and then we parse const argument, and you're wondering like what is const argument, and you go here, and here you see like an example what const argument looks like. Similarly, here we have like this like very complicated condition with like look ahead and like several branches and match here. And again, you can understand that, hey, this is the test for this particular match branch. So if we go all the way here, that means that we are parsing something like this. Like this is like with generic associated types, you can actually have like lifetimes before equality and whatnot. And like the second case is when you have like not equality but colon here. And I personally find this very, very useful when writing the grammar. And if you like look at the Kotlin parser and at most other parsers, usually people just write a fragment of a grammar there. But I don't find that tremendously useful because like grammar is very abstract and it's hard to understand what the code is supposed to do by just looking at the grammar. Well, maybe for some people it is easy, but for me it is hard. And in Rust Analyzer, like given that we have just an example here, it becomes blindly obvious like what this is supposed to do. So mod contents parses the contents of a module. And here is an example of module contents. Okay, it starts with parsing inner attributes. And then it parses items or macro invocations, because that's actually Yeah, because those things are items. Well, the last one is item. But the two middle one are actually macro invocations which may themselves expand to an item. And you see here, like, how do we actually do this parsing? Well, we do this until we hit an end of file condition or until we hit a right curly brace if we are caring about right curly braces. Because like this function works in two cases. First, it is like the contents of a source file, but it also is a contents of an item list inside the module. So if you parse like the file and you have an unbalanced right curly brace, you want to just resiliently skip over it and start parsing like the rest of the file. However, if you are inside a module with a curly brace, you actually do want to stop on this last curly. Okay, so I'm wondering like how far ahead should I go? Because I guess I've explained the overall architecture here. I explained this here, and we looked at a couple of parsing functions. What I want to do next is probably to just read through the actual parsing functions and explain step by step each case where we do error recovery or some other fancy things like precedence for markers, but that probably can be in a separate video. So let's actually make this a stop here and see you in the next video then. Thank you for watching. Goodbye.